My name is Michael Murphy. For you that don't know me, most people do. I'm with Murphy Brothers Contracting. I'm responsible for new project development, and I'm also part of the Village of Mamaroneck Microgrid Team. It was back in February of this year that we heard about NYSERDA and the state of New York were offering this, what they called the New York Prize. We thought, wow, this is interesting. And I took a look at it. I said, they wanted to, they were going to give grants for developing feasibility studies for developing community microgrids. And of course, I knew exactly what they were talking about. Actually, I had a meeting with Lois Arena from Stephen Weir Associates. She explained to me what microgrids were. She showed me the light, and I said, we could win this. And together we worked on the feasibility, or the proposal, and they accepted it. And so part of what we're doing here is we're raising community awareness amongst the design community on a presentation entitled Developing Community Microgrids. I'd like to thank our good friends from Coughlin Insurance. We have Mike Coughlin over there with his dad Jack, his son Case. Mike, you want to say a couple words about Coughlin Insurance?
Yeah, give me an opportunity.
They're not going to listen to everything.
No. We're property casualty local brokers here in Larchmont, and we've got an office in Manhattan and one out in California, in Calabasas. So we specialize in real estate for sure. We've got a homeowners division and just came out with a energy efficient product. We're the only agent in the country to underwrite with Pure Insurance Company a discounted energy efficient home program that we've got. I handle trade contractors, HVAC contractors, plumbing contractors. We do architects' errors and omissions. We are very competitive. We broker to about 25 different carriers on a daily basis, and I'd welcome a phone call anytime. Thank you very much.
Very good. Errors and omissions. Never heard of that. Anyways, little known fact. Mike Coughlin worked for Murphy Brothers Contracting when he was how old?
Yeah, 7. You guys. I wasn't sure it was legal, but you told me it was.
Yes, his dad said get a real job, a job before he would hire him back. So anyway, so thank you, Michael, and also
I'm Murphy Brothers Insurance Agent, which is
absolutely. So in the interest of full disclosure, and also another one of our sponsors is All Pro Cleaning and Restoration, and we have June Burke over here. Now, interesting enough, June, do you want to say hello, stand up? This is June.
I'll just say hi. We are happy to be here, to be a sponsor. We work with Coughlin. We are disaster recovery, fire flood restoration, mold remediation, reconstruction. So in the event of a disaster or the winter, you have pipes bursting, you know, we are claim-based predominantly. So hopefully you all have coverage for disasters. But
in the event of an emergency, June shows up at your house and everything
no,
gets much
I don't
better.
show up, but our company would. So 24 hours a day, 7 days a week, 365 days a year. So anything we can help you with, you know, our flyers on the back, and thank you for letting us do this.
Thank you. 2 names you should know is Coughlin Insurance for insurance protection and All Pro for the cleanup and that kind of thing. And a third name, Stephen Weir Associates, and we're so proud to have them here along with Sal Cohen in the back there from Intelligent, who's our cogeneration expert. We're going to start the presentation. If you need to use the bathroom, you know, they're outside and to the left over here. We have plenty of coffee. There's food over there. You can get up during the presentation and feed yourself if you'd like grab a bottle of water or whatever. And I'm going to turn it over to Jim Williamson.
Thank you very much. So, my name is Jim Williamson. I'm a mechanical engineer with Stephen Winter Associates. Stephen Winters is an engineering and architectural firm specializing in energy efficiency in buildings. For the past few months, I've been serving as the project manager on a feasibility study that is examining building a microgrid in the village of Mamaroneck. The agenda for this presentation is step through the following points. First, I want to provide a background of New York State's energy vision and how it's starting to evolve and how microgrids play into that. I want to tell you a little bit about what we are planning for the village's microgrid. We talk about the area and some of the challenges we've had and how we plan to generate the energy. And then I will give an overview of microgrids, just a high-level technical background explaining what they are, where they make sense, talk about the process of how do you analyze an area to build a microgrid, and we'll talk about the types of generation resources and where they make sense. And then I'll run through a few case studies that I think really pinpoint and show how microgrids are working and where they are making sense. So, New York State vision on energy is transforming. They have recently released plans for what they call their Reforming the Energy Vision, or REV. And the idea behind it is they've noted that we need a transformation in New York's energy policy. We have an aging infrastructure and a growing population. New York's arguably one of the most complicated grid systems in the world. And they're looking at ways to make this energy system more reliable, resilient, and affordable. And one possible solution to that is incorporating microgrids. So some of their main goals, just by the numbers, they want to reduce greenhouse gas emissions by 40% as compared to 1990 levels. They want to have at least half of the electric generation come from renewable resources. And in addition to modifying how we produce energy, they are also setting the goal of decreasing our energy consumption by 23% over 2012. So there's really two approaches here. We want to generate energy more efficiently, and we want to also use it more efficiently. I included a few metrics that kind of give a background of what energy use looks like in New York. Hopefully you can read this. A lot of small numbers. First, take the pie chart on the left. It shows the breakdown in residential, commercial, industrial, and transportation. The key takeaway is the majority of the three major players here are commercial, residential, and transportation, almost quantifying a third of all New York's energy use. The next figure I have in the top right shows how New York is generating its energy today. The power plants that are sending electricity to your businesses and homes, where is it coming from? Where the major sources are natural gas, nuclear, and hydroelectric. So there's somewhat of a diverse mix compared to other states. The last plot on the bottom, the chart on the left, something that you guys don't like, you can look at New York's energy bills in this, a percentage in dollars per kilowatt hour. You can see in the commercial and residential sector, we are near the top of the list, almost 45% above the U.S. average. This is another view to demonstrate what energy costs look like in New York compared to other states. So I took data from EIA, which is the Energy Information Administration, and I have the cents per kilowatt hour cost of energy that you pay when you pay on your utility bill. And I've ranked all the states in order. You can see New York is at the top of both these lists. The first one that I have plotted is all sectors, so that's kind of like a aggregated mix of that pie chart that you saw. That corrects for the percentage that comes from commercial, residential, transportation, etc. And then the similar plot for commercial. So the key takeaway here is New York energy prices are high, which you guys probably already know.
What's the reason, I mean, you probably could guess, what's the reason that Hawaii is so high there? Just to figure it out.
I think because they have to transport their energy resources a long distance.
Okay.
Why is New York so high?
And why is Connecticut so high?
Yeah.
Higher. I think
Because it's near Hawaii.
we'll get into that. But
Further away.
I think the difference demand, right? The demand was, right?
Demand, highest demand charge?
Yeah.
That plays a role. Let's hold questions towards the end, and I'll answer them all at once. 'Cause that can be a whole other discussion. Alright, so as part of this REV initiative, which was reforming the energy vision that New York laid out, one of the steps was this New York Prize competition. And this was organized by NYSERDA, which is New York's Energy and Research Authority. And they said, let's take a look at some target areas around New York State and see where it might make sense to be installing microgrids. I guess this is a good point to give you the baseline definition of what is a microgrid. Best simplest way I can describe microgrid is think of first a grid within a grid. But if we take a collection of buildings, a microgrid is a well-defined area, let's say 3 or 4 buildings. It can be any number, for example, 3 or 4. It has its own generation resources, and it has the ability to modulate its own consumption loads. And it can be wired into the grid so that it can act in parallel, or disconnected so it can act independently. And the idea is that you can form a larger grid by grouping many microgrids together, and they can operate when it makes sense for them to perform most efficiently. There's the New York Prize Initiative awarded 83 teams around New York State. You can see the blue areas are their target areas, and I think it's what they've identified as weak areas of the grid that could use improvement. And the yellow dots are the 85 different teams that were awarded feasibility studies to look at, does it make sense to install these microgrids? So the first stage of the process is strictly feasibility. Does it make sense? Let's look at some buildings, see if it makes sense technically and in terms of cost. Then there will be 2 more rounds that teams drop off as they select the best cases. There'll be next a design round, where they're really narrowing down design and getting into the specifics. And then lastly, 2 to 3 years from now, some of these will actually start to be built. I think before it really is easy to comprehend what a microgrid is, it's best to understand how our current utility grid system works. So here's kind of your stereotypical grid that we have in the US. We have big central generation stations that are stepping up voltage to high levels, are transporting energy over long distances, stepping the voltage back down, and then delivering it to businesses and homes at a usable voltage, 120 and 240. The vulnerability with this kind of situation is that you have several buildings on one dedicated transmission line or distribution line. So if that line goes down, all the buildings are up. This is a map that shows how our national electric grid is actually laid out. So it's not one big electric grid. It's actually divided into 3 grids. We have the Eastern Interconnection, Western, and then Texas ended up on their own somehow. But the takeaway here is that it's a complicated system, and there are thousands of miles of transmission lines that are running all over the country with our current system. So the idea behind a microgrid is getting away from this one huge central generator and taking a group of buildings and fitting in a few different generation sources that are smaller in capacity. They're different kinds of generation, and you can fit in generation sources that are efficient and optimize the type of energy use that you have. So here's the basic example of a microgrid. There's a group of buildings and they all have their own independent loads. And then within this grid, there's various generation sources. So examples, we have batteries included in here. You can put in solar, fuel-fired generators. And the idea is that you'll use these generation sources in an optimal way that suits your load. And you can also use them to strengthen the grid. So you'll connect to the utility grid, at least at this point that we are in the evolution. Taking this one step further from just a one building setup or a couple buildings in one group. So we have, down on the bottom is basic facility microgrid. So the way that I think of this is you have one building and one or two generation sources. But we want to make this concept modular so that it can grow and so that different buildings can help support each other to make their use most efficient. So the idea is that you can group different facility microgrids into one conglomerate community microgrid. So that's the second box. And then there will be several community microgrids that form to make our large grid. So the advantage here is you could also incorporate buildings that don't have their own generation sources, and you can utilize some smart meters to shut off non-critical loads during times when, say, there's a power outage on the grid, and you don't want to feed a non-critical facility. If you have a limited amount of power, you can incorporate the controls technology that they're coming out with now to cut off power to one particular building for that time being. So I put together a graphic that I thought kind of described what I'm calling the macro grid, or our current grid, versus the idea of a microgrid. So this macro grid, I would say each box represents, let's say that entire square is our current utility grid, and each box is a generation resource. So maybe a coal-fired power plant, a nuclear plant, hydro. The way that it is now, there's limited modulation capabilities. So say that one of the substations went down, and that means that an entire area is going down, because the central generation idea means that one generator is providing power to thousands of homes. I mean, the utility has backups included, redundant loops in their feeders to combat against it, but it's a vulnerable situation where that can happen. The idea behind a microgrid, same concept. Let's say each of these little squares are buildings with generation resources, is you could independently shut off resources when they don't make sense to use or they can't be used. So let's say those red resources are solar and it's nighttime, so you don't have any energy being generated. The surrounding generation sources in the grid can help to pick up the rest of that load, and the grid will operate as efficiently as possible. Sure, the question you're probably thinking is, why would we want to build microgrids? And there's a few reasons. One of the obvious reasons is it gives us the opportunity to generate power when the large grid goes down. And this can happen if we give it the capability to disconnect from the grid and act as an island. And that's why this idea has really piqued interest for the government to let it suit itself towards powering critical facilities. The next part of it is there's a lot of different ways that you can control it, but even if your grid cannot power your entire load, you can use it to shave off some of the peak of your load, which in turn will reduce your energy bill and provide relief to the utility, so they don't have a situation where they have too much current going through transformers or particular line sets. Depending what area of the country you're in, you can likely generate energy at a lower rate. probably likely in New York. We saw those rates. Having control over your own generation gives you a hedge against increasing utility rates. So if rates continue to rise, you'll have more control over how you generate your own power, and you're not forced to pay into that increase. Depending on what kind of resources you include in your grid, you can make a significant impact on lowering emissions, especially if you're able to utilize a lot of renewables. I think from maybe a community's perspective or a developer's perspective, having an uninterruptible power supply really increases the value of your area. It can bring in more businesses and probably residents, and I think it can really drive up an economy. And lastly, one point is, if this kind of a method evolves to something that can be repeatable, this could be a solution for solving our global energy crisis. This can be a repeatable way to deliver power to the 1 billion people across the world that don't have access to it, because it offers us the availability to start small and expand outwards rather than a huge infrastructure cost all at once. So why are we looking at putting a microgrid in the village of Mamaroneck? These are a few photos from a storm that they had, and it wasn't one of the huge hurricanes. My understanding is that it was something that was only supposed to be a moderate rainstorm, and because of conditions with how the rivers were running and the ground was frozen, the town was basically covered in 3 feet of water. And we can understand how this is harmful to the electrical layout. I think when Murphy Brothers saw this and they've lived in this area, they realized that this is a good opportunity to provide power to our critical facilities in the village. So we worked with them to identify a few facilities that were within a close radius that we could include in our microgrid. So initially we selected here's let me start. This is my "you are here" arrow, like got right, kind of like you're at a mall looking at the map. The buildings that we included as critical facilities are the police station, fire station, Village Hall, lmc-tv, 3 local gas stations, Arctic Glacier Ice, and then we have the new Murphy Brothers buildings included here as the plan A.
That's home base, that's home base.
This will be our place where we're going to house generation equipment. That's a major challenge with microgrids. Is if you're retrofitting equipment into an existing layout, you guys probably understand this a lot better than me as architects, where do you put this equipment? So part of it, as they're constructing new buildings, we are working with them to design them to accommodate the generation equipment. So right now we are looking at including the PV, photovoltaics, and cogeneration, which is a method to produce heat and electricity. We're still in the design phase and figuring out what makes sense as far as where the utility lines run and what we can group together. But this is the area that we're looking at right now.
Can I ask a question? That Sheldrake River, that wasn't what overflowed, it was basically Long Island Sound.
Okay.
No, let me beg you, it was the Sheldrake River, it was the Mamaroneck River.
Oh, it was all of them
It was
together.
all 3, yeah. What, are you speaking about the major flood?
Yes.
If I can interject here, and I'm sorry.
You would know better about that.
Okay, that was, it was a combination of heavy rains, ground that should have been thawed out by that time, and then it was the high tides. And what we experienced was, basically, it was all the runoff from White Plains. So,
The reason I'm asking is just down behind Majestic Kitchens is a major cable TV, Optimum Online, and I'm wondering why you didn't include them. Because that hits everybody in Westchester.
We're still in the process
Oh,
of
no, no, I'm
figuring
just saying
out
that
which-
maybe you can add that to
Okay.
the list, because that is a major cable. I don't know what LMC-TV is, but
They're
They're right behind you. This is LNC TV
I
right
don't mean
here.
that, no, I'm just saying, that's fine. I'm just saying that maybe that should be included, because that's a major provider of cable TV to Westchester.
Okay.
How about including the sewage treatment plant? Wouldn't that be a good one for a critical resource?
That came up also, and we're still, that is, suggestions are good for our feasibility study to figure out what makes sense.
One medical facility?
We don't have any medical in here now. I don't know if there are any. It's still evolving, and really the phase that we're at now is, does this make sense technically and financially? And part of that is selecting the right buildings in right here. Working on this project, these are the following team members that work. Murphy Brothers Contracting, which you know they have offered up their new building as a site where we can house generation equipment, and they will be involved in the construction process as this microgrid becomes built. Stephen Winter Associates, which is us, we have been spearheading the load analysis of the buildings, looking at utility bills, and coordinating with all the other team members. We are working with Delta Products, which is a group that is experts in microgrids and PV and battery storage and integrating all of them together. KTM Architect is helping us with the layout and to determine where we need variances if we're going to house generation equipment in the Murphy Brothers building. Sperry is our expert on controls and communications within the microgrid. So that's a major part of this. When you have a lot of different generation resources, you have to have them talk to each other. IntelliGen is our expert on cogeneration. And then, of course, we are working with the Village of Mamaroneck. And it's been great to work with them as they've really helped us to identify the critical buildings in the area. So, if you want to develop a microgrid, what steps do you need to take? I've listed them as 1 to 5, but this isn't necessarily a linear process. It's more iterative and get to step 4 and go back to step 1, and it's very repetitive. First thing you have to do is select a group of facilities. Once you've defined those facilities, you need to get out to the buildings and analyze them, see what's out there, and take a look at their utility bills. The next step would be looking at the surrounding existing utility grid to see if there are opportunities to use the feeder lines that were already run in the area to distribute your energy. Once that has been done, you need to select your generation resources. Are we using PV, wind power, battery, generators? And then the last step, once all this is figured out, is really nailing down the financial, legal, and business aspects. So what do you want to look for when you're selecting facilities to incorporate into a microgrid? So the path that we have taken is to include facilities that are critical to the area, facilities that you would want to keep open when the grid goes down. Your police stations, fire stations, those that can support the community. You want to select facilities that are within a reasonable range of each other so that they can actually be joinable. You can't have facilities that are 10 miles apart because you won't be able to join them into one microgrid. You will want facilities where their energy loads are large enough to make the installation of the generation equipment economically feasible. So if you have a building where the load is very minimal, you may not ever see a payback. But I guess when you're looking at critical facilities, the financials aren't always about dollars per kilowatt hour and payback in that period, because there's also a financial benefit of keeping those facilities open during storms when the grid is down.
Is there a radius that you recommend for these?
I think when we initially started talking, we were looking at a mile to a half-mile radius. But one of the next slides, I show how the utility grid kind of changes all of that.
Jim, if I can interject, when we first started with my survey, they said we haven't found it feasible to go outside a half a mile. So we recommend you don't look any further
That's
than
why I
a
was
half a mile.
asking, because
Yeah.
I don't think that they would accept something over, I thought it was gonna be 3/4 or a mile because it doesn't become financially feasible.
Right, that's what they said.
So
They said-
but you broke that mold in suggesting something a little bigger? Yeah. Sorry for opening up Pandora's
No,
box.
that's okay, that's just that, yeah.
So the other thing is when you're selecting areas that you want to target is to work with utility, to look at areas of the grid that might be weak. Maybe there's a set of buildings that are on the end of a feeder layout where it's a vulnerable area that loses power often, or an area that has poor power quality, and you can help control the power better. Lastly, you need facilities where there's actual space to put the equipment, which can be a challenge. Once you've selected your facilities, the next step is to look in how much energy do they actually use. And there's kind of 3 different metrics that drive this discussion. One is the amount of demand power that they use. So this is generally regarded as the peak power consumption over the course of a time period. In your utility bill, you'll see it monthly. But for this analysis, we also are concerned with what it looks like on a tiny interval, such as hourly. Because if we're incorporating something like solar, we need to know, is the load present when the solar energy is available? And then lastly, the common metric that you look at is your kilowatt hours, or when you're looking at the big collection of buildings, megawatt hours. Once you get an understanding of the loads that you have available, it's important to get out to each of these sites to see what's there. What kind of heating and cooling equipment do they have? Do they have any other generation that can be incorporated into the grid? And this is also an opportunity to seek out places where we can do energy retrofits. So this isn't only about generating more efficiently, it's identifying places where we can make consumption more efficient. So this, at Stephen Winter Associates, we work a lot with energy modeling. That's one method to look at different measures that you can implicate in order to reduce energy and what is most cost effective. So once you've kind of selected your buildings, the next step is working with the utility to see what the feeder looks like. How are the utility lines run? Say, before I started getting into this kind of work, I kind of envisioned the utility to actually look like a grid, which it doesn't. There is a combination of high voltage lines and secondary voltage lines. And it's not necessarily true that because 2 buildings are right next to each other that they're on the same line. So this takes a good amount of cooperation with the utility to see if I want to use the utility section, is it feasible or do I have to run my own lines? So I've included 2 examples that you might encounter. This is an example where you have a primary voltage line running down the road and there's a transformer in each building that's dropping it down to the usable voltage. One case there is you could put a switch on each end of the line in order to isolate your grid. Another example would be you come to a secondary voltage line and it's the end of the feeder. You could put a switch here and isolate your grid. Say this is probably a preferable situation because it doesn't interrupt any other parts of the grid if you just switch off this section. The key takeaway here is that just because 2 buildings are right next to each other, it doesn't mean that they will automatically be on the same feeder and you can just join them together. It takes a bit of analysis. So things that you will want to work with the utility to determine is what is the feeder layout? Where are their current switches? Are they available to use? How will we control this? And ultimately what we want to do is we want to create a situation where we can operate our microgrid so that it's in parallel with the grid. So here's a little diagram. Picture this green line as the grid, and this is our little microgrid. We have a generation source and our load, which is our buildings. We want to be able to switch it so it's islanded by itself, and also switch it so that it can operate parallel with the grid. When it's operating parallel with the grid, the next question that comes back is, can we export power back to the grid? And I think that's, the rules for that, since microgrids are kind of still evolving, are unclear on how the utilities will treat that. So the meat of your microgrid are the generation resources. And to talk through a few of them, we'll talk about fuel-fired generators and specifically cogeneration, which we have Sal Kona with us from Intelligent. He'll be able to talk through that. And then we'll mention some of the other resources that can be used, PV, coupled with battery storage. So these top three are the resources that we're considering in our microgrid, and we'll spend most time explaining. But then provide a mention of others that can be used.
So one of the most important parts of a microgrid is a cogeneration system. And mostly because it's power that's available 24/7, basically. And our systems run primarily on natural gas. They can be built in containers to be outside and various indoor units as well. So what is cogeneration? Basically, we're taking natural gas and we are converting it to make heating and or cooling and electricity. So it's one power source in gives you two outputs, and that's the term cogeneration, basically. And our systems are comprised of a reciprocating engine and a generator, and that's inside the box, and there's heat recovery in the box as well. So the engine burns natural gas, generates electricity, and that's one output here, and then the heat from the engine is converted, is captured and then transferred to the building. We can make steam with that heat and hot water. In most cases, we're always making domestic hot water for a building, and then a lot of cases we can do heating in the wintertime and cooling through absorption chillers. So one of the things that drives cogeneration is the spark spread. Okay, so that basically is the cost of natural gas versus the cost of electricity for an equal amount of energy being the term on this particular graph. So this is just demonstrating, and this is actually up to 2010. So this shows a trend of natural gas cost and electricity cost and the difference between the two. And that's really the takeaway from this slide. And the bigger spread here, which we call a spark spread, the more economically feasible a system will be. And all of these systems require a pretty fast payback. As you know, with other energy efficiency upgrades, there needs to be a good payback in order for it to happen.
And natural gas is going down now, right?
Yeah, and now if we extended this out to 2015, you would see a downward trend here a little bit. And that's what we...
So it's the biggest.
It's an even bigger spread today than it was in 2000.
Yeah, in years.
Well, we aim for paybacks that are under 5 years for a conventional cogeneration project. 4 years is a nice target, sometimes 3, usually in that range. And NYSERDA funding does a lot to help that. Just with sizing the systems, okay, we look at two things primarily. So this is the electrical layout of a typical building. They all typically look like this, and the numbers on the side vary depending on how big the building is. You have July and August being the peak demand period, and then the winter, obviously much less electrical demand. The inverse is true for heating. So your thermal is obviously much less in the summer, and that's typically representative of domestic hot water load, is that July and August thermal load, and then in the winter, you see it much higher. So we try to capture both in a sense where we want to size for at least the minimum thermal demand and just higher than the minimum electrical demand. And that's your conventional way of sizing cogeneration. You can see here, we pick that line right about there, the amount of thermal that we want to produce, and the electrical right about there. And that's going to be a really efficient system. We're going to be able to utilize the majority of the fuel year-round if it's sized this way. In certain situations in Con Edison territory, we're allowed to size it for a little bit larger to account for more of the peak demand. And they're doing that with NYSERDA with certain special situations. And that's just to increase the generating capacity of the entire city.
So the thermal load there for the domestic water, what type of building would that be? Is that like a hotel or?
That would be a hotel, or actually it would be a multifamily or a hotel.
Okay.
Would be a very similar profile. Any place where people are sleeping at night and taking showers and doing laundry, things of that nature. Those are all prime candidates. And thermal drives a lot of the payback as well.
Now, that line that you picked, is that a median or an average? How do you come by that?
Well, this is, in this line here, we're just showing
Is the maximum?
the minimum thermal demand. It's not really an average, it's just showing the minimum. And on the electrical, we're basically just picking a spot a little bit above the minimum demand as the starting point. And then, you know, we kind of go from here and see what makes sense. Other considerations play into this, like size, you know, space weight available, is gas available, and then other interconnecting issues.
And is the electricity AC or DC?
This is AC power. So we do have an inverter system which turns AC to DC
Yeah,
back to
that's
AC
why I was
again.
asking.
Yeah, there is a quote unquote DC link,
Photovoltaic.
similar to a solar, but we do put out ultimately AC power.
Just one question for cogeneration system. How do you go for the maximum peak demand?
Okay, so in certain situations, NYSERDA allows us to size for the peak demand. Okay, it really just depends on the building and because there's some economic factors that drive that. The benefit to that is then the system can give the building a full backup capability versus
In what
selecting
situation?
certain loads where you would be in that situation. So, but all that plays into a lot of other factors, being space and just how the building is wired and so on, what makes the most sense. Oh, yeah, sorry.
Is there a scenario for catastrophic failure? In the event that you can't connect to you're standing by yourself?
Yeah, the systems that we are designing today, which will be in this microgrid as well, are standalone systems. So they're designed to be in parallel with the grid, then also act as emergency power systems in case the utility fails. And that dual-purpose system drives pretty much everything we're doing today. The technology is all driven by that. The blackout of 2003 in the Northeast here made a lot of people realize that resiliency plays into all of this, and energy efficiency. So the two combined is really what cogen really lends itself to.
And what is the source of power when you can't use the grid?
Natural gas. So in this case, our generators are powered by natural gas. So they would need to have that source available 24/7. And that's part of the relationship we have with the utility, is to develop in places where that gas is available and feasible. And speaking to the gas side, our emissions are much lower than a utility generator would be. So our emission standards are 1/10 of what the utilities is today, but mandated by the EPA. So
Is
we're
part
clear.
of that also the transportation?
I'm sorry?
Well, you lose a lot of the power.
Correct.
created.
Through transmission lines,
Transmission.
it's talking physics. It's very inefficient to transport electricity via electrical lines versus transporting gas via a gas line. So that's really the principle that is making this work, is the efficiency side of it. I'm sorry.
I say the same thing.
Okay, sure. So basically, this is just explaining a little bit about where the utility prices are right now. If you're a building in New York City, okay, to heat your building, let's say you're paying around $1.20 a therm for gas, and you know you're paying somewhere around 20 cents per kilowatt hour of electricity. So you're in this box right now when you're just buying from the grid. what the cogen unit will do is allow you to buy, your electricity at a much lower rate, which, basically would be somewhere around the 8 to 10 cents per kilowatt hour mark. So when you buy natural gas on the preferred cogen rate and you convert it to electricity, you're going to be generating at about, give or take, around 8 cents or so, versus around 20 or so cents, between 24 and 16 where you're buying now, depending on the time of the year. And the cogen gas rate is steady throughout the year, it doesn't fluctuate. So, this graph just shows where you would be. You want to be closer to the 3 to 5 year payback, and you don't really do jobs that are outside of this 10-year payback. And that's basically it.
Thanks, Sal.
Yep. Thank you.
So the other part of our resources, a major component, is using PV, which everyone is probably familiar with. PV, these are the types of arrays that you might see. Include this picture because I think it's interesting. It's a developer that we worked with in Massachusetts who didn't have space available on his roof, so he was able to fit it on a carport out in the parking lot. This is around a 30 kilowatt system. The basics on how PV works: the sun is radiating energy, average of 1,000 watts per meter squared, down towards the earth, and a PV cell is able to utilize that energy to knock free an electron out of a semiconductor, and from that to create energy. So inside of a PV system made up of individual cells, which are assembled into modules, and then when you lay them out on your roof, you would have the array of PV modules. The interesting thing with PV is how much the price has dropped over recent years, and I think this is really driving why it's becoming a cost competitive measure to install, to provide your own electricity. You can see back in 2009 we were almost around $8 per watt, and today we've creeped under $3 a watt, probably around $2.50 by now.
Without incentives, too?
This is with incentives.
And the incentives have gone down.
And this is a crucial time because the federal incentives are on their way out in 2 years from now. PV and battery storage make a great couple. The reason being is that the obvious thing with PV is sometimes the energy is generated when you don't need to use it, and incorporating a large battery array into your system gives you the availability to store that energy that's generated. This plot gives a few different scenarios of maybe what a typical day would look like. This blue line is your energy demand, your electrical energy demand throughout the day. Sort of exaggerated here. General profile, you would see solar becoming available in the morning, peaking midday, and then settling down as the sun sets. The idea is that the PV would be able to sustain your whole load here, but during these periods, the battery would discharge. The battery could become recharged during this period where there's excess solar, and then again used during this period. And you can use other strategies, discharging the battery when it's favorable to reduce your peak load. Some other resources that other microgrids have used, but we aren't currently considering: fuel cells, wind turbines, biomass, hydro, which is actually a good portion of New York's current energy production. One of the most important parts once you have your resources in is having them communicate with each other and communicate with your buildings and the loads in your buildings, and also communicating with the central command center of the utility. This diagram kind of maps out how that might behave. You have your home area network, which is with your facility microgrid, have PV and a CHP system. There is a controlling hub that is your microgrid controller that is interfacing with other facilities to form your community microgrid. And these different resources can work to support each other and benefit each other so that it's operating in an optimal way. And the system will communicate with the utilities control center, which is pictured here. Could be through, they can send a signal through the power lines, it's called power line communication, or you can use a Wi-Fi option. These are a few control strategies to consider when you're using renewables. First one on the left here, demand charge reduction. These peaks here are points that will accrue demand charges on your utility bill. And you can use renewables, discharge a battery during this period to basically drop those demands down and ultimately reduce your bill and reduce the load on the utility lines. Similar situation, using batteries to kind of, at this bottom left, to kind of smooth out the resources available by renewables. So when you have solar or wind, the amount of energy delivered isn't always constant. It's based on how much wind or sun is available. You can use batteries to smooth out the energy output. Peak shaving. And another important control aspect to look at is your frequency regulation. So in the US, we operate at 60 hertz. And when you have renewable systems that are running at variable rates, you need to put attention towards using a master frequency to have a constant power quality if you're supplying it back to the grid, and also to protect your loads. As with any project or investment, financial considerations play a huge part. The interesting thing is that in microgrids, there's currently a good amount of incentives to help this financially. They have incentives for cogen, PV. They have incentives for demand reduction. Use a variety of equipment types. Certainly depends on your local utility rates, how much you're paying, and your dollars per kilowatt hour to see what the payback will look like. What the load available looks like. Is there enough energy load to actually see the payback? And do you have an opportunity to drop that demand lower? Something that's still being figured out, kind of in the microgrid realm, is how do they handle exporting power back to the grid? Do you get the same rate as other power generation facilities, or how will that be handled? And then how simple is it to integrate with the existing utility lines? If you have an ideal situation at the end of the feeder, you may be able to put in one switch, an exaggeration, rather than if you have facilities spaced all over the place, you may need a whole conglomerate of switches to actually make the system work. Some of the challenges that you see when you're looking at microgrids is getting the public and the customers to be comfortable with the concept. It's hard to take a utility grid that we've had for a century and say, okay, we're going to change it now, and really relaying how this change is a benefit. It's challenging to find adequate space, whether it's for fuel-fired generators or PV space on rooftops. It's challenging to find an ideal distribution network based on what's existing in the utility lines. Understanding legally how these operate is a whole nother game. So we're going from an existing utility that's very regulated and the government is involved in controlling rates and who owns what. And when private investors go to owning microgrids, that's a whole new aspect to the game. How is that handled? And you're always looking to optimize efficiency. You have this challenge, you have loads that you can modulate, you have generation sources that you can modulate. How do you design it and operate it so that it works as efficient as possible? So, I've compiled 3 case studies that are both in being built and just finished being built, that are similar to what we're looking at in the village and kind of show that these are possible and they're starting to be built. So, interestingly, Connecticut actually is just at the end of their microgrid feasibility study. They had a similar process, and they're just at the end of year 3, and the first ones are being built. One of them is in Milford, Connecticut. It's kind of between Bridgeport and New Haven, right along the shore. So their critical facilities are a government center, middle school, senior center, and city hall. And they are also using cogeneration units, PV, and battery storage. That seems to be a model that other areas are finding that works. This is an interesting case study. The Marine Corps in San Diego at one of their air bases.
Is it Pendleton?
This is Miramar.
Miramar, okay, it's the airport.
But they have kind of taken an aggressive goal to make 50% of their energy consumption renewable, and they've incorporated a lot of different generation sources to do this. And one of them I found interesting is they have a landfill on site, and they're able to use the methane coming out of the landfill to power, I think it was almost half of their total load. It was impressive. And it's a different source that you don't see often. Another microgrid in the process of being built, Fairfield, Connecticut. You guys are probably familiar with, right near Bridgeport. They are including their police station, fire station, and a public shelter. Again, this is similar to the approach that we're taking as far as the facilities we're considering. And they are, again, using a combination of CHP and PV. As a recap, I hope that I've answered these questions for you guys. But first, what are microgrids and how do they work? See, a well-defined set of buildings and generation resources that is controlled to work optimally and most efficiently and can be grouped to be part of a larger grid. How can microgrids benefit the community and strengthen the surrounding grid? This is providing power during periods when the grid is down, reducing energy costs for customers, and can reduce load on the grid by producing when energy is most optimal for your select generation resources. How do you analyze a set of buildings for inclusion in a microgrid? It's based on the buildings that you choose. Typically, it makes sense to include critical facilities at this point as the microgrid phase is just gaining ground. And you want to look at what are the utility bills, what's at the buildings on site as far as generation resources, and how easily can they integrate into the grid. And the bigger picture is how can this be turned to be financially feasible. And then on cogeneration, what is cogeneration and where are its best applications? Cogeneration is a method for using natural gas to produce both electricity and heat. And the best applications are where you can use the full amount of heat and electricity both generated to work at very high efficiencies. And they are optimally sized by looking at your thermal load and selecting your baseline thermal load and sizing the system to that, so that because the thermal load is generally higher than the electrical load, then you can use the electrical load to drop your consumption costs. So, thank you for your time, and if you have